So, good afternoon, everyone. So, today we will study braking of an induction motor. Okay. So, the following methods are employed for braking of induction motor. First one is regenerative braking. So, as name suggests, the power flows back to the supply. Okay, from the motor. Second is plugging. So these are all similar to braking of a DC machine. Okay, in plugging we interchange the phase sequence, and third is dynamic braking. Okay. In case of dynamic braking, we disconnect the supply given to the stator and we connect a resistance. Okay. So these are three braking, and the dynamic braking can be categorized into some more classification. Like first is AC dynamic braking. Second is DC dynamic braking. Third is self-excited braking. Using capacitor. And fourth is zero sequence braking. So these are the various methods which are employed for the braking of an induction motor. Okay. So as we studied this earlier, in case of braking of a DC machine. Okay. So in case of regenerative braking, the motor is supposed to operate as a generator, and power is the power flow is reversed and power is fed back to the supply. In case of plugging, the two phases of motor are interchanged. Okay, and in dynamic braking, we disconnect the supply given to the stator of the induction machine, and it is connected to a braking resistance. Okay, so first we will study regenerative braking. Okay. So whenever the speed of motor becomes greater than synchronous speed, okay. So speed of motor omega m is greater than synchronous omega s, synchronous speed. So it will behave like a generator. Okay. Let's suppose there is an example, lowering of load in case of lift and hoist. Okay. So if there is lowering of load in case of lift and hoist, the speed of motor will become greater than synchronous speed because it is under gravity. Okay. So the speed of motor will become greater than the synchronous speed, and it behaves, and motor will operate as generator. Okay, and power flow will be reversed. It will be from generator to the supply side. Okay, so if the speed of induction motor is greater than synchronous speed, then it will behave like a generator, and there will be a regenerative braking will be there. Okay, and also when power input is given by root 3 into V into I into cos phi. Okay, so this is the line voltage and this is line current, and this cos theta is the input power factor. Okay, so if for motoring, this phi is less than 90 degree. Okay, so cos is less than 90 degree, we will get positive power, and if speed is become greater than omega s, then relative speed between rotor conductors and air gap will reverse. Get reversed. Okay, so relative speed between rotor conductors and the air gap power reverse. So the current will reverse. So current will get reversed. Rotor current will get reversed. Induced voltage will be reversed. Ampere turn will be reversed. Okay. So in this and in this case, so phi will become greater than 90. Okay. So power factor angle will become greater than 90, and now P in will become negative. Okay, because cos phi, which is greater than 90, will give you negative. So power is negative, means power flow is in reverse direction. So it will flow from generator to the supply side. Okay, so this is known as regenerative braking. Okay. So when induction motor is fed from constant frequency, okay, and it is the motor is made to rotate above synchronous speed. Okay, so then we will get regenerative braking is possible. Okay. Now we will see the torque speed characteristics. So next axis torque, in y-axis it is speed. Okay, so the speed torque characteristics. This is our normal speed. This is origin minus e, and this point corresponds to e. Okay, so this is speed torque characteristics of an induction motor. Okay, so this will. So at the time of starting, slip is equal to 1, and when slip rotor speed is equal to synchronous speed, slip is equal to 0. Okay. So when rotor speed become greater than synchronous speed, okay, so this will enter to second quadrant. Okay, so this is first quadrant and this is second quadrant, and the characteristics will be something like this. Okay, so this is negative torque. Torque is negative. slip in this case is negative. Slip is less than 0. Okay. So now torque is negative. The torque is negative. So power will also negative. As we seen earlier also. So power is negative, and this motor will behave as a generator. So this is regenerative braking. And this first quadrant is of motor. Okay. So, how to make, so in this case, when there is a lowering of load in case of lift and hoist, and how to make the speed greater than the synchronous speed. So, we know that relationship between rotor speed ns nr is equal to 1 minus ns, 1 minus s into ns, and this is equal to 120 f upon p. Okay. So by changing frequency and number of poles, we can change the speed. Okay. And here, what we'll do, we connect the induction motor with a inverter. So we, as we have seen earlier, so this induction motor is fed with inverter. Okay. And this is rectifier. DC. And 3 phase. Okay. So by using this V by F inverter is equal to constant, we can have speed greater than synchronous speed. Okay. So so we seen this earlier. This V by F control of induction, speed control of induction motor. Okay. If V is kept constant and F is decreased, okay. So this is equal to, this is proportional to flux phi. So flux also decreases. Okay. So beyond the base speed, so this is the case. This is V and this is F. So this is our base speed. So beyond this base speed, if F is increased, F is increased, so flux will decrease and the speed will increase. Okay. So by giving this variable frequency and variable voltage, this is VF voltage. So the commands to this induction machine are variable voltage and variable frequency, and here frequency is increased and voltage is kept constant. Okay, so it is proportional to plus 5. Okay, so this will give to field weakening zone. Okay, and speed will increase. Okay. So we can vary the frequency of the output voltage and voltage of the output voltage in such a manner, if frequency is reduced, so motor will be raised. Okay. So when frequency is increased, so rotor speed will also increase. Okay. So when rotor speed increases, so torque becomes negative and it enters to the second quadrant. Okay. And there is power flow reverses. Okay. So as NR is equal to 1 minus S into 120 F upon P. So frequency is increased, so the speed also increases. Okay. So here, what is the advantage of this method? So power is getting fed back to the supply. So this is the advantage, and disadvantage is that you can't use this regenerative braking less than base speed. Okay, so this is only possible beyond the base speed. Okay, so below base speed, this regenerative braking cannot be applied. So this is the only disadvantage, that below base speed, the regenerative braking cannot be operated in case of three-phase induction. Okay. So now we will see the second braking, that is plugging. Or reverse voltage. Second is plugging or reverse voltage braking. Okay. So what we do in this plugging, we interchange two phases of the induction motor with respect to the supply terminal. Okay. So phase sequence of the supply is changed, which is applied to the stator of induction machine. Okay. So let's suppose this is the induction motor, and it's the motor terminal. This is R, Y, and B. In here, these are happy, right? Let's suppose these are the supply terminals. Okay, so we will connect this R from B dash and Y from this R dash. Okay, so this will be dash. This is B dash. Okay, so this is the case. So we are interchanged the phase terminals of induction motor, and we have interchanged it, and this R is connected to Y dash and Y is connected to R dash. These are supply terminals. Okay. Three-phase supply. So when the phase sequence is changed, so rotating the get reverse. So phase sequence phase sequence is changed when rotating magnetic field also get reversed. Okay. So let's suppose if the area rotating field is rotating in clockwise direction, and when we change the phase sequence, okay, so now it will rotate in anti-clockwise direction. Okay, so if we suppose this is forward in rotating in forward direction, so now it will rotate in backward direction. Okay, so here we are what we are doing, we are interchanging the two motor phases, okay, with respect to motor terminals. Okay, so let's suppose we will draw its speed torque characteristics. Okay. This is T, this is origin, this is C. This is first quadrant, this is second, and this is third quadrant, this is fourth quadrant. Okay. This is minus omega n. Okay. So now we will draw the speed torque characteristics. So as we see here, so this will be the speed torque characteristics of normal induction motor. Okay, normal operation of the motor. Okay, now the phase sequence is reversed and rotating magnetic field is also reversed. So the speed will become now minus omega s. Okay, so speed will also changes. Okay. So now when this is omega s positive, and when the rotor magnetic field is reversed, so now we'll get, suppose this is minus omega s, so we will get this type of characteristics, okay, in third and second quadrant. So this is natural characteristics. Okay, and if we add some resistance in rotor side, so this type of braking, that is plugging, is normally applied in case of squirrel cage induction motor. Okay, so this is the rotor. So we insert this resistance using slip ring. So we have inserted this resistance to the rotor with the help of squirrel cage. Okay, so as slip So now slip will also change, as slip is equal to omega s minus omega m divided by omega s. Now slip becomes negative, so speed is also negative. So this is minus omega s. So this will be this can be written as 2 omega s minus omega s minus omega m divided by omega s. This will be equal to 2 minus s. Okay. So slip for the backward rotating magnetic field will be 2 minus s. Okay. So slip will be equal to 2 minus s for the reverse field. Okay. So now, as the slip is become 2 minus s, so the induced voltage will be doubled. It will be approximately doubled. Okay, as it depends on slip. So induced voltage is increased to double, and so we have to insert this rotor resistance in such a manner it should be twice of the starting resistance. Okay, so it can withhold some current, braking current. So the braking resistance must be twice of the starting resistance. As slip is now 2 minus s, so this is equal to somewhat 1.9 and 1.96 and in that range. So this the induced voltage will be doubled. Okay, current will also increase heavily. Okay, so we have to ensure the braking resistance must be nearly twice of the starting resistance. So it can withhold, it can hold this high current. Okay, so we have to ensure this to limit the braking current to the starting value. Okay. So now, if resistance is introduced to this rotor with help of the slip ring, so now the characteristics will change. Okay. So this is without resistance is introduced, and these are the characteristics with external resistance. Okay, so let's suppose this is characteristics 1, this is 2, and this is 3. Okay, and we suppose a constant load torque PL is like this, characteristics of load torque PL. So this will be the operating point A. Let's suppose this is operating point A. Okay, so this is our operating point A, the intersection of load torque and the speed torque characteristics. So the operating point is A. So when phase sequence is reversed, so rotating magnetic field also get reversed. So this will enter to second quadrant. Okay, so this will enter to second quadrant, and let's say this point, this new operating point as B. Okay, so and the rotor due to inertia, the speed will be remain constant. Okay, the speed will remain constant. Okay, and the operating point will shift from A to B when phase sequence is reversed. Okay, and due to the high mechanical time constant and the inertia of the motor, so speed will cannot be changed immediately. So this will be the speed of the motor will remain same, but it will shift from first quadrant to second quadrant. And here the torque is negative. So here torque is negative. So motor will now deaccelerate. Okay, and this will follow this curve. So motor will now deaccelerate, and from this figure, it is quite obvious at zero speed, torque is not zero. It has got some torque. Okay, some negative torque. Okay, so here when the characteristics enters to the second quadrant and torque is negative, so this will deaccelerate the motor and it will now follow this curve, and at this point the speed is 0 but torque is not equal to 0. Okay, so we have to disconnect the supply at this point. Okay, let's suppose this is point C. Okay, so we have to disconnect the supply. Okay, so we have to disconnect this supply at point C. Okay, so we will disconnect this supply. Okay, so if we disconnect the supply, the speed of torque, the speed of the motor is 0, and the torque will also get reduced to 0. Okay, so in order to stop the motor at this point, at point C, we have to disconnect this motor. So we require a detector which detect the 0 speed. Okay, so this detector will detect the 0 speed and it will disconnect these three supply terminals which are connected to the motor. Okay, and if we don't disconnect the motor at this point, so this will be continue to accelerate in the reverse direction. Okay, and it will enter to the third quadrant, which is reverse motor. Okay. So we use a device which detects 0 speed, and it will detect the 0 speed and it will automatically disconnect the three motor terminals which are connected to the supply side. Okay. So if we are not disconnecting the supply at point C, so motor will now enter to third quadrant. Okay, which is reverse motoring, and it will accelerate in the negative direction or reverse direction. Okay, and if we connect the rotor resistance, leading rotor resistance, so now the characteristics are shown in dotted line. So now the operating point will shift to some new point. Let's suppose this as point D. Okay, so now the operating point will be shifted from B to D, and again it will decelerate. Okay, like this, and at point E will get 0 speed. Okay. And again, if we have 0 speed detector, it will detect 0 speed, and we disconnect the motor from the supply, and the motor can be stopped quickly. Okay, so this method is used to stop the motor quickly, and but a disadvantage is there. So we are connecting braking resistance, so there will be heavy I square R loss in the rotor. Okay, so this is the disadvantage of this method, but you can stop the motor very quickly. Okay, so if the motor is not stopped at point D, again it will continue to accelerate in the reverse direction, and it will move along this curve, okay, in the reverse motoring mode. So this plugging involves very large amount of current because slip is 2 minus s, and rotor current depends on this. So rotor current also get double. Okay, so we have to ensure that there must be a sufficient resistance which can limit this braking current. Okay, so which is quite large. So this is generally used in slip ring induction motor. Okay. So now this is all about the plugging. Now we will move to third braking, that is dynamic plugging. Third is dynamic braking. And in this case, motor supply is disconnected. Motor terminals are disconnected from the motor supply, and the kinetic energy of induction motor are dissipated in the braking resistance. Okay. So the first type of dynamic braking, so we will discuss. First type of dynamic braking is AC dynamic braking. Okay. So what we have 3-phase AC supply and an induction motor. Okay. So this is the stator and this is rotor. And rotor is short circuited with help of slip rings like this, and this is phase A, this is B, and this is C. Okay, so this is motoring on. Okay. So what we do in case of AC dynamic plugging, so we remove one of the phases of induction motor. Okay. Like this, we have disconnected phase A, and phase B are still connected to the rotor, and phase C also. This is B and C. Okay. So here phase A is disconnected, and B and C are still connected to the induction motor. Okay. So this phase A is open circuited, and through slip rings now we will insert some resistance, external resistance. Okay. So this is the case. Here phase A is open circuited and phase B and phase C are connected to the stator of the induction. Okay. So in this case, so IA current will be equal to DC as it is open circuited, and this type of connection is known as two lead connection. Okay, we have got only two terminals connected to the induction motor, so this is referred as two lead connection. Okay. Okay, so when this one phase is open circuited, so this will lead to unbalanced condition. Okay, so here phase A current is equal to 0. So IB will be equal to minus IC. Okay, so this will lead to a unbalanced condition. Okay, so the two phase current IB are equal and are opposite. Okay, so these are connected to single phase supply. Okay, and the motor is considered to be fed from positive and negative phase sequence voltage voltages. Okay. So what will the positive phase sequence current? IP, this will be equal to 1 upon 3 IA plus alpha IB plus alpha square IC. Okay, and here IA is equal to 0 and IC is equal to minus IB. So positive phase current will be equal to 1 upon 3 0 plus alpha IB minus alpha square IB. Okay, this is 1 by 3 alpha minus alpha square into IP. Okay, so alpha is equal to e to the power j 2 pi by 3, and so substituting here you will get alpha minus alpha square cos 2 alpha by 3 plus j sin 2 alpha pi by 3 minus cos 4 pi by 3 minus j sin 4 pi by 3. Okay, so these two get cancelled and you will get 2 root 3 by 2. So substitute here. So IP will be equal to 1 upon 3 into root 3 into IP. This is J. This is equal to J by root 3 into. So positive phase current IP is equal to JIB by root. Okay, and so what about IN? IN will be equal and phase opposite to IB. So IN will be equal to minus J IB by 2. Okay. So if we derive the negative phase sequence current IN will be equal to 1 upon 3 IA plus alpha square IP plus alpha IC. So when you solve this, you will get minus J IB upon root 3. Okay. So what we get? So negative positive phase sequence is equal and opposite to negative phase sequence current. Okay. So an equivalent circuit diagram can be drawn, keeping this in mind that IP is equal to minus IN. So this will represent a series network, series connected network. Okay. So this is the equivalent circuit diagram. So this is RS, stator resistance and leakage reactance, and then we have magnetizing reactance. This is leakage reactance of rotor. Okay, this is RR dash on S. This is XM, and this is XS equal to B, and then again XM. This is XS dash. So XR rotor side leakage reactance, and this will be RR dash divided by 2 minus S. In case of negative sequence, so this is equivalent circuit diagram. Current, so this is IN, this is RS XS, and this is I. So these are equal and opposite. Okay. So this is the voltage across the positive sequence network is VP, and across negative sequence network it is VN. Okay. It is for positive sequence field. Okay. And it is for negative sequence field. So corresponding to VP, positive sequence voltage, will get TP, positive sequence torque, and corresponding to Vn, we get En. It is negative sequence torque, and this is positive sequence torque. Okay. So once we get this equivalent circuit diagram, and we have got this, and voltage across this is V, and we have this is V. Okay. So we have to derive this voltage. This voltage given to this circuit diagram. So voltage applied to the series combination. So this will be VP minus VN. Okay. So this will be VP minus VN. So this will be the voltage applied to the series combination. Okay, so this is 1 upon 3 VA plus alpha VB plus alpha square VC minus 1 by 3 VA plus alpha square VB plus alpha into VC. Okay. So here VA is equal to 0. Okay. So you get 1 by 3. This is alpha minus alpha square VB plus alpha square minus alpha VC. Okay. And this can be written as 1 upon 3 alpha minus alpha square VB minus VC. Okay. And this is J by root 3. We have calculated it, and this will be V. Okay. So this will be equal to JVBC line current divided by root 3. Okay. So once we got this voltage and this network, okay, for negative sequence and positive sequence, we can easily calculate this torque, and the net torque will be summation of the positive sequence torque and negative sequence. So net torque will be equal to Tp plus Tn. Okay, and you can find the current also. Okay. So we can calculate current and torque by using this network. Okay. So now we will draw its speed torque characteristics. So this is similar to the analysis of single phase induction motor. Okay. Hence it is connected to a single phase supply. Okay. So this will be torque speed characteristics under AC dynamic braking. Okay. This is omega s. This is minus omega s. Here, similar type of characteristics in the negatives. Okay. So this is Tp, positive sequence torque, and this is negative sequence torque En. Okay. So this is your origin, and if our constant load torque is taken, this is T1, so this will be the operating point. Let's say it is so intersection of this speed torque characteristics and load torque is the operating point 1, and the resultant of these two torque give the resultant torque. Okay, and the net torque, and the rotor resistance is taken such that the torque which we will get so we will get this type of this is our net torque. So the rotor resistance is taken such that we get negative net torque. Okay. So we have to insert such a resistance that we will get negative torque. So the rotor resistance is very high. Okay, so get effective motor braking. Okay, so if we choose the resistance which is not large enough and the net torque lies in this first quadrant, so there will be no load. So we have to ensure that sufficient resistance must be inserted in the rotor side with help of slip ring, so that the characteristics of the net torque lies in the second quadrant, that is in braking region. Okay. So this we have to load. So for positive speed, torque should be negative. Okay. And now, this characteristics will enter to second quadrant. Okay, due to rotor resistance, let this new point, operating point is 2, and here torque is negative, total torque is negative. So motor will be accelerated, and this will follow this curve, and this will become 0. And here torque and speed both are 0. So there is no question of reverse speed. Okay, so this will become 0 here. Okay, so for AC dynamic braking, the characteristics change from first quadrant to second quadrant. Okay, let's suppose this point 1 is operating point and it will shift to new operating point 2, and here the torque is negative in this region, so the motor will deaccelerate and it will come to 0, and at this point at origin torque is also equal to 0, and it will not go further into the reverse motoring mode. Okay. So by suitable choice of resistance, braking torque can be obtained in entire speed range. So here, choice of rotor resistance is very important. So this will ensure that there will be effective AC dynamic braking will happen. Okay, so we have to choose such high resistance that the characteristics of net torque will lie in second quadrant, that is torque should be negative. Then only we can get the braking of this induction motor. Okay, so this is all about DC. Second two terminal, two lead connection operation. In the next class, we will proceed further and we will discuss the third lead, three lead connection. Okay, thank you, class.